So in this problem, we're told that we have a right triangle whose legs are labeled as x and y. We know that x is increasing at the rate of 3 centimeters per second and y decreases at the rate of 2 centimeters per second. And we want to know how fast the area of this right triangle is changing when x equals 25 centimeters and y equals 50 centimeters. And so we're going to use the chain rule for functions of multiple variables to solve this problem. So here's what we've got. We've got the area of this triangle, which is going to be given by 1/2 x times y. So the area is a function of two variables, x and y. Now, x and y depend on time, so let's call time t. So x depends on the variable t, or you might even want to think of it as a parameter t, and y also depends on the parameter t. So this looks a lot like the situation we had, the diagram we had for the chain rule when we have a depending on two variables and then each of those depends on a single variable. So when we're asked how fast the area is changing, you know that a rate of change can be thought of as a derivative. And so this is how fast a is changing with respect to time. So what we're looking for is the derivative of a with respect to t. So what we're going to want to do is find the partial of a with respect to x, the partial of a with respect to y, the derivative of x with respect to t, and the derivative of y with respect to t. Now, since a depends on two different variables, these derivatives are partial derivatives, so that's why I'm using this partial derivative notation. Now, x, as far as we know, depends only on t, and the same for y, so these are the plain old derivatives that you did in Calculus 1 and 2. Alright, so I gave you we know what the formula for the area is in terms of x and y, so we can determine these partial derivatives fairly easily. Now, I didn't even give you a formula for x in terms of t or y in terms of t. So how are we going to find these derivatives? Well, they're given to us. We know that x is increasing at 3 centimeters per second. That's the rate at which x is changing with respect to time. Right? In fact, even the units are a unit of distance over a unit of time. That's dx dt. And then this is going to tell us what dy dt is. Alright, so let's put all this back together. So we need the partial of a with respect to x. So we treat y as a constant, and that's going to give us 1/2 y. And we need the partial of a with respect to y. We think of x as a constant, and so that's going to give us 1/2 x, I think. And we are given values for x and y. X equals 25 centimeters and y equals 50 centimeters. So this is 1/2 times 50, and that's going to be 25. And I think that that's going to be just 25 centimeters for dA or del A del x. Now del A over del y is going to be 1/2 times x, which is 25 centimeters. And that's going to be 12.5 centimeters. How am I getting these units? Well, a is measured in square centimeters, and x is measured in meters. Right, a is measured in square centimeters, and x is measured in centimeters. So centimeters squared divided by centimeters is just centimeters, and the same thing over here. All right, and so dx, so that's what, so del A del x is 25 centimeters, and this is 12.5 centimeters. Now dx dt, that's the rate at which x is changing. We're told it's increasing at 3 centimeters per second. dy dt, y is decreasing at 2 centimeters per second, so that's going to be negative 2 centimeters per second. Negative because it's decreasing. All right, so we've got everything filled in now. All we need to do is multiply and add. So remember that what we want to do is trace out all the paths from a to t. We're finding the derivative of a with respect to t. So we have this path down here, and then we have this other path that goes from a down to t this way. So we multiply the derivatives along each path and add the results. So when you multiply these two together, you're going to get 75 square centimeters per second. And when you multiply these two together, you're going to get minus 25 centimeters squared per second. And so that turns out to be 50 centimeters squared per second.